Good morning, everyone. I'm happy to be invited here today to give a talk about my research work. My name is Shiyu LIU. I'm a third-year PhD student in ARMEN research team, LS2N laboratory at Centrale Nantes. My thesis topic is decentralized control and robust observer of a flying pilot robot interacting with the environment. Maybe a few words about me and my research team before talking about this topic. For my education background from 2012 and 2017, I was involved in a dual diploma program. I was doing my bachelor's degree at Northwestern Technical University in China, and I was pursuing an engineer's diploma at INSA Lyon in France. So in the last 2 years of this period. And after 5 years of studies in mechanical engineering, I found that I'm now really into it. So I chose to do another master's degree in robotics at University of Montpellier too. After that, I was lucky enough to stay at the laboratory where I was doing an internship. So I work as a research engineer at ISTIA Montpellier for 1 year. Then after that, I realized that there is still quite a lot of things I don't know in robotics, but I would like really to work in this domain in the future. So I came back to continue my studies by pursuing a PhD degree at Centrale Nantes from 2019. So the team where I'm in is ARMEN. This is a acronym for Autonomie des robots et matrice d'interaction avec l'environnement in French. So our motivation is the design and control of the robots interacting with the environment. As you can see in these images, we have been working on quite a large range of robots, like manipulators, aerial robots, and autonomous vehicles. We also propose new designs of robots like this new type of parallel robot and the flying parallel robot, which is my thesis topic. We also deal with the control and perception of the robots. And particularly in the drone group, we are mainly working on the design, control, and perception of the air robots, just as what I said for our research team. And currently, we have 3 main PhD theses. Like here, this is a flying gripper. I will mention it later because it is highly related to my topic. And also, we have 1 PhD students working on drone formations in which multiple UAVs are controlled their intern formations by an NPC controller here. And also the flying parallel robots is my PhD thesis. In our group, each year we also propose quite a lot of master projects. Like here, there have been quite a lot of projects working on aerial cable turn system. So it is a system where multiple drones are supporting a payload by using of the cables. And this year we have 1 project working on drone detection using deep learning algorithm. And also we have 1 student working on the drone flipping. So this is a real-time simulation environment for validating his controller. So now, just align with our motivation, my thesis is about a flying parallel robot. It is a new robot design with 3 drones. So in the following, I will talk about the thesis motivation, giving some modeling and control background, and also the main parts of my work is the decentralization of the robot and robot environment interaction. And finally, I will give some conclusion and perspectives to finish my presentation. So first, let me give a quick talk about the context of my thesis, the error manipulation. Actually, this domain is an emerging domain where the ARMEN aero vehicles UAVs are equipped with robotic arms or end effector for grasping, transporting, and manipulating objects. As you can see the example here, a very simple ways of designing such robots is just to combine a multicopter with a classical robotic arms. So it has been there have been quite a lot of architectures proposed in the literature for aero transporting, grasping, and even for aero writing tasks. However, these kind of designs present some drawbacks, like as the payload limit, payload capacity is limited by the thrust limit of a single UAV. And also, as we know, the multicopter UAVs are under-actuated systems, meaning that the thrust force they can produce is always vertical to the body frame. So the manipulation tasks are quite constrained by this limit. Therefore, a new class of the aero manipulators has been proposed. We call them multi-UAV parallel robots. In this design, multiple UAVs are connected to the platform or to the payload by multiple UAVs using the cables or rigid links. They show their strengths in the aero manipulation domain because of the high payload capacity and the full manipulability in three-dimensional space. As I mentioned before, the Flying Gripper is also a new robot design we worked in our team. There was a PhD student just graduated, and in this design, four quarters are used to drive the platform collectively, and there is a gear and worm mechanism underneath each quarter. So beneath we mount the grippers, and they can be driven by spinning the quarters. So no additional motors is needed in this design. However, the limitation of the current work on multi-UAV parallel robots has been that they all depend on motion capture systems. It is an external localization system in all indoor environments. So also there is a lack of consideration of the significant robot environment interactions. So the motivation of my thesis is to propose the decentralized control of such robots without the need of any external localization systems, and also to accomplish real manipulation tasks that can be performed by the FPR. So before talking about the main contributions, I will present the detail of the flying parallel robot by providing the modeling and control background. The FPR is actually an analogy to parallel mechanism, but with the fixed actuators replaced by UAVs. So the FPR prototype we worked on is composed of a moving platform and three rigid legs that are attached to the platform by means of regular joints, 1 degree of freedom joints, and quarters are attached to the other end of the leg by spherical joints. So this design, the original design is proposed in this master thesis and by this paper written by the previous PhD students in our team. So the rest of the presentation will have quite a lot of equations, but I will try to be brief and not to lose the generality of the talk. So the robot pose, the robot configuration of this robot is composed of the platform 60 pose and the leg angles. The PP is the position of the platform, and with respect to a reference frame F0, and HP is actually a unique quaternion to represent orientation. And the robot velocity can therefore be given by the linear and angular velocity of the platform, as well as the leg angle rates. As for the only actuation of the system, the thrust forces are produced by the quarters, and we denote it by Fi for each quarter I. And the position, orientation, and linear velocity of each drone can be donated by Pi, Hi, and Vi. Also, Hi is the quaternion represented orientation. Here, a remark is that all the variables we present here are defined with respect to a common reference frame, F0. But if we lose the external localization system, this frame is meaningless. So in the next section, I will talk about how to deal with the reference frame if we have no longer the external localization system. The modeling of the FPR can be presented by its geometric, kinematic, and dynamic models. So I will just present a little bit more about the dynamic model. It's actually built a relationship between the input force, the thrust forces of the quarters, and the accelerations output of the robot. And M is the generalized inertial matrix, and C is the vector of Coriolis and Coriolis vector. With J is the Jacobian matrix relating the velocity of the FPR to the linear velocities of the drones. As for the controller, we use the dynamic model to compute the thrust forces needed with an auxiliary input U. This U is computed by an PID regulation to minimize the tracking error towards the desired trajectory defined here. And KP, KI, KD are positive diagonal matrices for PID gains. Then after F is computed, we can extract each Fi for drone I, and the desired thrust and attitude, desired thrust magnitude, and the desired attitude of each drone can be further calculated, which are then sent to the inner loop, sent to each drone and regulated by the inner loop thrust attitude controller. So this is then overall workflow of the control. So first we have a offline trajectory planner to define the desired trajectories, and outer loop is used to compute the the input forces based on the trajectory tracking, and then we compute the thrust magnitude and orientation, the desired attitude of each drone, and then sent to the inner loop attitude controller. So let's now move on to the main parts of this presentation. The first part is the decentralization. As I said before, the first motivation is to decentralize the control of the FPR, because in the centralized chain, all the robot states is captured by the motion capture system. And also a centralized computer runs the controller and communicates the control signals with each of the three drones. This is extremely sensitive to the communication delays or interruptions. So what we want to achieve is to first reconstruct the robot state without the motion capture system. So by using onboard measurements distributed on each drone. And Secondly, the controller is preferred to be implemented onboard each drone, probably with or without the communication between them. As for the distributed measurement, the aim is to deploy the onboard and intrinsic measurements to reconstruct the robot state. So we propose to mount a pinhole camera on each drone, which is able to measure the relative pose from the drone frame to the platform frame, represented by this rotation matrix. Then, together with the IMU sensor measurements, we are able to reconstruct the platform orientation. So we start by proposing the measurement of the internal configuration, the leg angles. It is previously done by the geometry model, knowing all the body poses by the mocap system. And for now, the leg angle is actually known if we know the relative pose between the platform and the drone eyes frame. This relative pose can be presented by these homogeneous matrix composed of rotation matrix and translation vector. And we found that this relative pose can be estimated by onboard camera using some techniques like the model fitting techniques or accrual marker detection technique. Then for platform's orientation, it is previously expressed with respect to the initial reference frame F0, but which is no longer available for now, since we consider that there is no external localization system. However, we noticed that the onboard IMU measurements can provide well-estimated roll and pitch angle of the drones. And along with the relative rotation between the platform and each drone measured by the onboard camera, we can at least reconstruct the roll and pitch of the platform. But to express these roll and pitch angles, we introduce two flat frames since we have no longer this reference frame. We call them flat frames, FFI and FFP, attached to the platform frame and each drone's frame. These flat frames have zero roll and pitch relative to F0 and an unknown relative yaw with respect to the F0. Actually, these frames can be seen as here. The transparent platform there is a flat frame attached to it. Furthermore, we found that this flat frame can be used as a common reference frame. So we use the flat platform frame as the reference frame for expressing all the robot states as the velocities of the robot. Finally, we are able to reconstruct the roll and pitch of the platform, the leg angles, leaving the platform position and yaw as unknown values. After having reconstructed a partial set of robot coordinates, we now consider how to better control the robot with these variables. So we propose to control the known variables by their desired values and unknown variables by the derivatives. As a result, we can formulate a new vector of the controllable coordinates set, Xi. It is composed of the linear velocity and yaw rates of the platform coming from the unknown values, and roll and pitch of the platform and the angles. Finally, this is an easily teleoperable system with an operator defining the desired Xi and Xi dot to get the partial information on the desired trajectory. And just as I said, the unknown P and Psi is controlled by the derivatives, and the known values are controlled by the desired values. Then we also deploy the controller in a decentralized manner, which means that each drone performs its own measurements and implements its own controller onboard the drone. Based on the controller itself is not differed as in centralized control, but compared to the centralized controller, it is obvious that the decentralized controllers are more robust to the communication delays or interruptions. And for computing the control on each drone, it will require the information on the other lag angles, theta j, and the linear velocities of the other drones, Vj. So based on whether this information is available or not, we propose two decentralized controllers. Sorry, named C controller and NC controller. In C controller, all the drones exchange the most recent measurements between each other, and in NC controller, the information of these zeta j is always the desired values computed from the teleoperation command. We have conducted experiments to verify our controller. The first one, I need to mention in this preliminary experiment, we still use the mocap to emulate the camera's data by adding representative measurement noises that can occur in the real detection case. So two experiments were conducted. The first one focused on the control of the internal configuration and platform orientation. And in the second, a precise precision task is performed by teleoperation. So I will show you some videos of the experiments. This is showing the control of the internal configuration and platform orientation. We can see in blue curves representing the leg angles, and red for roll of the platform and green for the pitch of the platform. In both cases, both controllers can well check the desired commands sent by the operator. And in the second experiment, we perform the precision task by placing the platform underneath the three tennis balls hanging in the air. The plots here are showing the positioning error of each task. Once the positioning error falls down below the 10 centimeters, the operator is given 10 seconds to try to pick up the ball. And if the ball is picked up successfully, we can see that the positioning error is stabilized and within 5 centimeters, showing that it is a successful task. And during the whole experiments, we performed 7 positioning tasks towards 3 markers in a loop. And both controllers are successfully accomplished the tasks, showing the precise positioning of the platform by television is achievable. So now let's move on to the second part, which is a recent work that I've done. The current control strategy I presented have shown its effectiveness in controlling the robot in free space. However, it is no longer appropriate if we consider a significant robot environment interaction. As you can see in these examples, it is a previous controller dealing with an additional mass attached on the platform. So we can see that the platform is no longer can be controlled stably, because the flight is a simple hovering flight, but we can see there is large orientation errors, also the large leg angle errors. During the interaction, the robot is usually subject to the disturbances such as the winds, ground effects, and the uncertainties on the drone thrust, and also coming from the modeling errors, as well as the potential interaction range, meaning the force and moments exerted on the robot. An interaction control strategy should be able to properly react to all these influences coming from the environment. To do that, we should at first have the knowledge of the external range exerted on the robot. So we applied an external range observer to reconstruct all the external terms that present in the system. Actually, based on the dynamic model, we know that the robot should perform in a certain way. And if the output performance is not exactly as what we expected, we should be able to estimate the external terms that affect the robot. So we include this tau E in the dynamic model for representing the external forces or moments acting on the robots by the environment. Just as mentioned, we found that if we know the system input F and the actual response of the robot, its position and velocity, we can estimate this external range tau E hat. So this estimate obtained by the observer can further be fed into the controller to regulate the interaction. After having the knowledge of the external range by the observer, we should consider how to control the robot in consideration of the interaction. As I said, the aim of the interaction is actually to make sure compliance behavior when the robot interacts with the external environment. The impedance controller showed the strengths because it regulates the interaction force by a virtual mass spring damper system. So it is, of course, not a real mass spring damper system, as we know it very well in mechanical engineering. But the controller can regulate the robot behavior to behave as such dynamic system during the interaction with the environment. So here, the impedance behavior can be written in this matrix form, with MD, KD, BD are the positive diagonal matrices for the desired mass spring and damping coefficient. And epsilon tau here is the external range tracking error. With the minus tau E hat is the reaction force or moments the robot exerts on the environment. And the tau ED is the external range that the robot is expected to exert on the environment. So the complete observation and control framework is shown in this block diagram, similarly as what we have seen in the control background. And offline trajectory generation is defining the desired trajectory. And an observer is applied to estimate the external range and then sent to the impedance controller. So the later just computes the control input, the thrust forces F, and the rest of the workflow is quite similar. And some experiments have been conducted to verify the interaction control strategy. We first perform a hovering flight in addition of the load, and we also conducted a contact-based interaction with the environment, as we can see here. So two contact-based tasks were performed. The first one, we tried to interact with the board, wooden board in flat orientation, and in the second, this board is inclined at an angle of about 25 degrees. So as we can see here, the board is installed stably in the air by the stretched ropes. So in the first experiment, we showed that the impedance controller still stably control the robot with the disturbance of the additional mass, while the PID controller, we have seen that it is no longer working. We actually also performed the hovering flight with external winds generated by the fans. And the impedance controller is also better in terms of the tracking error. During the second experiment, we demonstrate that both tasks can be well performed by the FPR. So the impedance controller is trying to regulate the robot pose towards the desired interaction pose, while an operator is providing the desired force the robot exerts on the environment. Although we only did a contact-based interaction experiments, the method we presented can be extended to accomplish more complex tasks, which are potentially achievable since the external wrench acting on the full degree of freedoms of robot state is estimated. So finally, some words to end up my presentation. In the previous works, we have proposed a methodology to control the multi-UAV pilot robots without the dependence on external localization systems. Although we still use the mocap to emulate the camera data, the method can be easily applied to the real detection and estimation system by the real onboard cameras. An impedance controller along with the external wrench observation technique has been proposed, showing the effectiveness of the controller for the environment, for the robot environment interaction. Future works will focus on the implementation of the camera-based post-estimation technique or other more robust technique, just as I said, to accomplish a fully mocap-free version of the control. And more robust observers and controllers are envisaged to control the robot to accomplish more complex tasks with better precision. So thanks for your attention, and this is all for my presentation, and I'm happy to answer your questions.
Okay, thank you very much, Shiyu. So we have time for questions. So feel free to ask to Shiyu.
Hello, can you hear me?
Yes.
Yes.
I have a question. First of all, I want to thank you for this very informative presentation, Shiyu. It was very interesting, and hopefully at the end of first or second semester, I will get a fully understanding of what you're doing. So my first question is, as a first-year master student, I have to, I don't have 40 or 50 hours a day, so I have to eliminate some of the courses and focus more on the other courses. So which courses or which subjects, which key elements would you suggest for a beginner to put more focus on to make a study like yours? For instance, would you put more emphasis on kinematics or more on the control side? What would you suggest?
Yeah, it's a good question, because for me, I don't have a clear answer to this question. I also often ask to myself what kind of subjects I really love. So as suggestions, I propose you to open up your mind. So try to be at least knowing about the not every details, but the overall things on the different subjects. because I don't know which subjects you really like to work on, like the perceptions or the control side or the modeling side, because yeah, they are quite different in some aspects. But as for robotics, I think they are kind of related to each other, so you can get some insight from another topics, like for my robots, I should know about the modeling. I should even though the main works is on the control part. Yeah, so I think the answer is you should try to find the answer of what kind of the subjects you are really want to focus on.
Thank you so much. Can I ask another one?
Yeah.
What are the tools,
Yeah,
like
yes.
softwares, like what are the skills do you think we should like learn beforehand? Because I have seen some graphs and I want to know which software like did you do them at?
Okay. As for the techniques or the skills, I think the programming skills is really necessary and useful. If you want to work on the robotic systems, we should know the programming. We should be good at programming. So like the graphs or like the controller is written in C++, and all the figures I presented is written in Python. So I think for beginners, you can start by working on by your own the programming skills. Yeah, this is what I can give you as advice.
Thank you so much. And my last question is, what are your future plans? Like, do you think of moving to industry? And if industry, what is which companies, or do you want to stay in the academics?
For me, I would prefer to work in industrial, because my thesis really is not theoretical fundings or something like that. My thesis is really to make this robot work and to implement it. So I prefer to work in the industrial to implement things. Yeah.
Thank you so much.
Thank you. Thank you for your questions.
Okay, thank you for these questions. So we have time. Any other question to Shiyu? Maybe Shiyu, I want to ask you a few questions. So, basically, with the help of the camera, what is needed for you? Is it the pose of each UAV, or you have to measure the interdistance, so by making detection of the other UAV?
By using cameras, we are not detecting the other UAVs. We try to mount a camera on each of the drones. So the camera is measuring the relative pose between the platform and its own frame. So it's measuring.
Okay.
It's detecting the platform rather than the other drones.
Okay. And yes, because you saw yesterday the presentation of Guillaume Caron. So the question is that, do you plan, from your opinion, would it be better to use some fisheye camera or large field of view camera, or do you plan to use classical camera? What do you think about that?
I haven't tested, but for me, the problem is the field of view. If the classical camera is like the leg angles in my robots are limited, quite constrained. like within the 0 to pi minus 2 degrees, radians, sorry. So if the platform is always within the field of view using the classical cameras, why not using it? But if sometimes the platform is no longer inside the camera views, so probably it's better to use a fisheye or other cameras.
Okay. Okay. And if I understood well, you don't use any communication between the UAV, right? You don't communicate any position or information?
We don't communicate the position, but in our controller, sorry, let me come back. Yeah, we are in our works, we propose 2 decentralized controller. So first we communicate between the UAVs this information. So because on each UAV we measure the lag angles, and we also have the linear velocity of each UAV measured by the IMU sensor. So in the first controller we communicate this information, but we also found that we can propose the non-communication method in which the UAVs assumes that each of the other UAVs perform or tracked well the desired states. So in these designs, we just use the commands, the desired commands to compute the theta and the VJ of the other drones. And yeah, so both cases are achievable.
Okay. Okay. Great. Great. Thanks a lot. Any other question? Yes. I will turn off my macro. Yes. Can go.
Hello, I have a question.
Yes.
To my understanding, it looks like the model is based around taking the 3 drones and translating their motion through the legs into the platform. Do you think there would be a way to model it, or I guess at least design the controller such that you start with the platform position and then translate through the legs to the drone, so that way they have to hold, say, an XYZ coordinate? Or is that something more feasible only with mobile?
Sorry, I'm not sure I'm understand your question. You mean that we transport the platform first and then I'm sorry, can you repeat your question again?
Yeah. So to my understanding, it looks like the drone, like the system is modeled in a way that the controller starts at the drone level and translates their motion up to the platform in order to balance it that way.
Yeah.
Would there be a way to model or design the control law so it starts at the platform's position and then relates it down to, say, an XYZ coordinate of each drone, such that they only have to hold that position? Or is that something only feasible in mocap?
Okay, I understand your question. Yeah, it's a good point. We also discussed with a colleague because for now, the drone, as you said, there's a lot of echoes. For now, the drones are considered as the thrust generators. So we don't care about the position of the drones because they are attached to the leg end. So their position is really related to the dynamic model of the whole system. Yeah, you are true that we can start from the position and orientation of the platform and compute the XYZ coordinates of the drone. And after that, we control the drone in position of that. But the one problem is that the drones are now flying. How to say that? The drone are connected to the legs, so there are some physical interaction force between the drone and the legs, and this force is unknown. We cannot compute it based on the drone's model. So if we control the position of the drones, this force will always there as a disturbance to the position controller. yeah, so I don't know if I answer your question or not, but yeah, it is a direction of how to say, improving the current control of the FPR actually. Yeah.
Thank you.
Okay, perfect. Any other question?
Yeah, I
Shiyu?
have a question.
Yes, please.
Hello.
Yes.
Yes. Did you run any simulation before trying it on real?
Yes. As I have mentioned, one sentence. Yeah. Yeah,
Okay.
we have actually a real-time simulation environment. It is called Gazebo. So yeah, this is only for flipping of one drone, but we have also implemented a simulation environment for the FPR. So all the controllers I run in real was tested in these simulation environments beforehand.
Okay. Thank you.
You're welcome.
Thank you. One more question, maybe?
Could you ask a question?
Yes.
Yes. Yes, please.
I think in your research, 3 drones were controlled. I am very interested in the situation where more than 3 drones it can be controlled or not. So do you have some opinions about this?
Yeah, we use 3 drones simply because it is a fully attributed system, because we have a 60-degree of freedom on the platform and 3 degrees of freedom on each of the legs, and each drone can produce 3-dimensional force. So 3 times 3 is 9. This system is fully attributed system. We don't have problems of the over-attributed or under-attributed things, but it is possible to have multiple drones. Yeah, like more than 3 drones. But we should have to deal with the over-attrition of the system.
Okay. Thanks.
Thanks. Yeah.
Okay. Some question again. We have some time, so feel free to ask any other question.
Okay, I will ask one thing. Was it a big
Yes.
change going from gazebo to the real world? Like the physics and all that made you change it a lot, or was it pretty similar?
Sorry, I cannot hear you very clearly.
Is it working?
Yes, we just missed the beginning of your question.
Oh, okay. Sorry. Like, is it a big change to go from gazebo simulation to the real world? Like the physics and so on, did you have to make any big change?
You mean from the you ask about the difference between the simulation environment and the real world, right?
Yes, like going that step forward.
Okay. Actually, as for the control part, this is not much differences, because the simulation, it is really a the gazebo environment is really a real-time simulation environment. Like the drones models is just as the same as run on the real drones real drone board. But the difference is more, we found that the difference is more related to the communication. Like in this environment, you don't have any communication delays, or even the measurements noises is really low. Maybe you can set some measurement noises, but it cannot be always representing the real world noises. So yeah, coming from the simulation environment to the real world, we really struggled a lot, mostly on the communications part.
Okay, thank you.
Okay, thank you. Any other question? Maybe Shiyu, could you detail about the technical aspects of the UAVs for people? Are there commercial UAVs, quadrotors, or do you made them? Could you maybe
Yes.
detail?
Okay. Actually, these UAVs are custom UAVs. Quarters we buy it. It is called Crazy 25, and but the onboard attitude controller we use is open source PICSOC using the PX4 softwares. Yeah, so it's open sourced and very stable, I would say, for the control of the UAVs.
Okay.
Maybe
Okay, thank you. Yeah, any other question? That's okay. Okay, so thank you very much, Hugh, for this very nice presentation.